And here it is, the final boss itself. Our job? Prove that the square root of 2 plus the square root of 5 is an irrational number. Now, what makes this one so tricky, what makes it the boss, is that you've got two different separate roots in there. But don't you worry, we've got a plan, we have a strategy.
And our strategy, our key to victory, is this really clever technique called a proof by contradiction. Honestly, this is one of the most powerful tools a mathematician has, period. And today, we're going to put it to work.
So, what exactly is it? It sounds complicated, but the idea is actually pretty simple. To prove something is true, we're going to start by pretending it's false. We'll say, okay, let's just assume for a minute that the opposite is true. Then, we follow that logic, step by step, until it leads us somewhere totally impossible. Something that just breaks math. And when that happens, we've found our contradiction. That's the moment we know our first assumption had to be wrong from the very start.
Okay, strategy session is over. It is time to execute the plan. Let's walk through this thing together, step by step, and let's take this problem down. So here's our 4-step attack plan. First, we're going to make that sneaky opposite assumption. Second, we'll square both sides to simplify things. Third, we're going to isolate the one piece of the puzzle that's causing trouble. And finally, step 4, we expose the contradiction for everyone to see. Ready? Let's go.
Okay, step 1. We assume the opposite. So we'll say that root 2 plus root 5 is rational, and we'll just call it r. Now for step 2, let's square both sides. And you got to remember that old formula, right? A plus b squared equals a squared plus b squared plus 2ab. So applying that here, we get root 2 squared, that's 2, plus root 5 squared, that's 5, plus 2 times root 2 times root 5. And look at that, it simplifies down really nicely to 7 plus 2 root 10 equals r squared.
Awesome. Now for step 3, we have to isolate that last remaining root, the root 10. So just like you see here, we just do a little algebra. We subtract 7 from both sides, and then we divide everything by 2. And that leaves us with the square root of 10 all by its lonesome on one side of the equation.
And just like that, we've backed our assumption into a corner. This is it. This is the moment of truth. We're about to see the fatal flaw in our logic. So pay close attention to what happens next.
Okay, here it is, the big reveal, the contradiction. Look at the left side of our equation. We've got the square root of 10. Now, is 10 a perfect square? Nope. So we know for a fact that root 10 is irrational. But, now look at the right side. Remember how we assumed r was rational? Well, that means r squared is also rational. And if you take a rational number, subtract 7, and then divide by 2, guess what? The result is still rational. So do you see the problem? We've ended up with a statement that says an irrational number is equal to a rational number. And that is just impossible. It's a complete logical breakdown. It cannot happen. Which means there's only one possible conclusion. Our very first assumption, that root 2 plus root 5 was rational, it had to be wrong. It was false from the very beginning. And there you have it. That's the checkmate. Victory. Because our assumption led us to something impossible, the exact opposite has to be true. Therefore, the square root of 2 plus the square root of 5 is, without a doubt, irrational. Boss battle complete. So, hey, let's just take a quick second to appreciate what we've all accomplished here. With that final problem solved, you've pretty much conquered the biggest ideas in this chapter on real numbers. Let's take a look at the new tools you've added to your mathematical toolkit. I mean, think about it. You've totally mastered the factor tree for breaking down numbers, you've learned that super important HCF LCM formula, and now you know how to prove a number is irrational using this awesome proof by contradiction method. Seriously, you are ready for pretty much any question on this topic they can throw at you.
But you know, a true master never stops practicing, right? So to make sure these new skills are really locked in, I've got a few final quests for you. Think of it as a final practice set to really show off what you can do.
All right, here's your first mission. Your job is to prove that 3 root 7 is irrational. You can use that exact same proof by contradiction technique we just went through. Mission number 2 is pretty similar, but we're throwing some addition into the mix. This time, prove that 5 plus 3 root 2 is irrational. Again, just assume it's rational and go find that contradiction. And for your last mission, I want you to show that 1 over the square root of 3 is irrational. Now, I'll give you a little hint on this one to get you started. Try rationalizing the denominator first. Trust me, it'll make the whole proof a lot easier to handle. Oh, and before we wrap up, here's one last little bonus fact to add to your toolkit. It's a good one to remember. For any fraction to be a terminating decimal, one that just stops, its denominator has to be in the form of 2 to the power of n times 5 to the power of m.
Basically, only prime factors of 2 and 5. Just tuck that little nugget of info away. It's super useful.
And that's a wrap. We are done. That's it for Chapter 1. You faced every challenge, you learned all the techniques, and I can officially say you have conquered real numbers. Seriously, congratulations.
So, we've wrestled with all the weird mysteries of real and irrational numbers, and we definitely came out on top. But, you know, the world of math is, well, it's huge. Which leads to the next big question. What kind of secrets are hiding inside of polynomials? We're going to find out next time. I'll see you then.